basket. Can you read? Can you read? Is that too light? That's dark enough. You learned this before? Yeah, this is the very well-known. Those are very well-known equations for everyone if you are in the field of electronic engineering or electrical engineering. If you learn something about electrical, EE, let's start from the 4 equations. Especially for our lab, we are doing the high frequency wireless. Of course, you use the EM wave, right? You should understand that. To understand, this is the fundamental knowledges, and you know what to do. Take my best. Going to ask you more fundamental questions before we start, because I need to know what you know, then I can start. By the way, you can refer to your textbook. When will we when will everyone get textbook? When? Textbook.
什么时候书会到？
礼拜一。
Okay, so you guys don't have textbook.
刚上课的时候拿来。
Okay. Next week.
Yeah,
after you have your textbook, you can refer to your textbook. Before our midterm will totally, if you understand chapter 1, then you can pass the midterm, okay? You can understand just chapter 1, and of course the basic knowledges. And I will still, I will try to explain something, because this is a very high level course. There are many things you should understand before we start, like vectors. Those should be the basic knowledge. This is not new, should not be new. But maybe you have different memory about a vector, it's okay, because different field. We are talking about the electronic magnetic field, so we use our the field, the vector of field. Okay? Okay. Okay. First of all, we start from one charge. I have an electric charge. You guys understand what is electric charge, right? If you have a path, and you have a lot of electric charge pass through maybe the intersection of the surface divided by time, that is the current. That's how we define the current. Okay? If we have the electrical charge here, and we put, if this one is fixed, not moving to anywhere, is fixed, the position is fixed, okay? If I have an electrical charge here, the electrical charge has one, how to pronounce, column, how to pronounce? Column, the column, is that correct? Column, okay. Column, one, the Q column is 1. Here. Then, if you put another electrical charge, another electrical charge here. This one is fixed. The position is fixed. This charge will be moved, right? Everyone has this common sense, right? Because of, is there any slang or something like that? We said that how to say that? 正极相斥，负极how to say that? 同性相斥，异性相吸。Is there any slang for that? No. If you put a positive charge here, you will encounter a force push this charge away. Okay? Yeah, of course we know this one. And the force, how large it is, it depends on the force. The unit is Newton. How hard this push you away depends on, first of all, how much your Q R is or whatever Q. If this one is Q and this is a small q, right? And is okay. Again, this is if this is not one column, you have Q column, and then you put a charge has small q column here. So your charge will encounter a force which is large Q times small q multiplied by the surface, the spherical surface, 球面积, the area of the spherical, which is 4 pi r squared if the distance is r. Okay? And if this force, these two charges, they are existing in the air. If the material is air, so there is another constant we call epsilon 0. Okay. Did you guys learn this before? This is the beginning of why people can they discover, oh, there is an electrical force between this one, because you cannot see anything about an electrical the E field, right? You don't see anything, but you feel like something there because of this rate charge. Then you will encounter the force. If you are close, the distance of r is smaller, your F is larger, right? So people, they do the experiment and then they have this equation. They are very great people, right? Okay, they can do this one. Even for me, maybe it's very hard to repeat, right? How can you find a charge and then you define this, how many columns for them, then you know this equation? I think that's spectacular work. Okay, this is the first thing. You know the force. Okay. So you can imagine that, okay, maybe there's something happen because of this rate charge. Something magic. We call this something magic, which is isotropic and homogeneous, because this is an applied charge here, and the only thing difference is between the distance between these two charges. If you put that here, it's okay, but the distance is different, so you will have a different F, right? So this environment, this rate magic, we redefine it. We call that E field. This one can, see, it's, if we don't care about what you are, we don't care about what you put here, we try to normalize the result. Because if you have more this green charge, you have the result, the force will getting linearly increased according to, if this is 2, then you have the twice of the force, okay? So you write down this one, then you have E is equals to the big Q divided by epsilon 0 4 pi r. This is the E field. Okay, not yet. Those are totally wrong. Why? Because the vector cannot equal to the scalar. Understand? Vector should equals to a vector. So you need to write down, maybe this is R and this is R. R is the direction outside the charge. Okay? This is not XYZ. You can define the R. Okay? This is the original theory about electrical field. Okay? Understand? Okay, you don't need to remember the equations. You don't need, because this is, I think those are the equations in the 电磁学 EM class, electromagnetic class. Yeah, yes, those are basic electromagnetic. I try to review those things you are supposed to understand for this class. Okay, this is the E field. Furthermore, you will feel like there are something the same at different location according to the distance between the two charges. There is a location. You will find out that if you put the charge very close to here, the force is very large, which means there is a potential. We call, maybe you say that, voltage potential. When that, in that position, very close to your center, the potential is very high. Okay? So we will redefine another function, which is a scalar function. You can write down, maybe you already knew this one, that you will know E equals to minus gradient. This is why we say I want to teach you gradient at the beginning. To the V. V is a function. Maybe it's a function of R, or maybe it's a function of X, Y, Z. It's a position. According to the location, the position of your voltage, it will become the function of voltage. Okay? You take the gradient and you take a minus because the direction of the E is outside, but if that is close to your center charge, you have higher voltage. Okay? Understand? Okay, so this is the original theory about the electric field. Okay, then we can start. So, for the part one, before midterm, I'm going to tell you, like, first of all, I will introduce you Maxwell equations. We are going to use these four equations again and again until you can remember like me. If you use that again and again, maybe you think, oh, what are those? Because you don't know what are those, though, it's very hard to remember. But for me, you already know why we use that. You do that again and again, you can remember. Okay, those are the beginning of this class. Those are Maxwell equations. And use the Maxwell equations, we can solve the boundary condition problem. After you solve the boundary condition problem, maybe we will just pause. We will wait. We will use the boundary conditions after when we trying to explain a waveguide. For a rectangular waveguide, a very special kind of microstrip line, transmission line, a very special case of a transmission line. So we will use the boundary condition later after your midterm exam. But I follow the process of this textbook. You can check in chapter 1, they introduce this one and this one, this one. Anything maybe you don't understand, that's why I require you to buy your textbook. Then you have something to refer to follow, okay? Okay, if you don't have textbook, maybe sometimes you got lost from the class. Okay. Try to buy a textbook and follow my lead, follow what I'm teaching you. After a boundary condition, then I will derive the wave equation from Maxwell equations. Waves. Yeah. You don't see, you cannot see the waves. Those are invisible, right? You don't see E and H field. No, you don't see that. Those you think those doesn't exist? No, you can find it exists from something. What are they? What kind of the structure? How do you explain that in math? I will explain that in the next one. Then after you can derive the wave equations, we can try to describe a simplest case of wave. Okay? Can you follow? I try to explain from very general equations first. Okay? I apply the equations to have some boundary conditions. Those are the first part. Then the second part. After that, I use Maxwell's equations to describe the derived wave equations. Then we can describe the simplest wave. Then, okay, then you know something, which is the simplest. Okay, those are the things I'm going to do. I don't know how many weeks we will take. It depends on your feedback. Sometimes I will see how much you can follow. Okay, Maxwell equations. Yeah. Yeah, Rob? I see it's okay, right? My equations totally accept. Okay, now after I write down equations, I have to explain what are those. Last week we already explained the operators, curl and the divergence already, right? In a textbook, you will realize something. Like I like to write down this arrow thing like for the vector. Those are, I think it's more common, right? Everyone write down vector like this way, but I don't know why in this textbook. In this textbook they use only one bar. I don't know why, but those are totally the same thing. Okay? Vectors, 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 vectors. Those are the notations, different notation, but both of these notations are vectors. Okay? You just if you see this one, this is totally the same as the vectors I used to. Okay, vector function. If you take the curl of the E field, it will become something. If you take the curl of H field, it will become something. Okay? Those are okay. But second part is a little bit different. For me, I will remember like if you take the divergence of something is very they have a relationship to E field, which is D. And then there's another notation, B, which is very similar to you do something. You are talking about H. Okay, let's do this first. Because if you have the electric field or magnetic field, they exist not only in the air, right? Maybe they are in the space we call a free space, in a how to say that, vacuum, 太空，在太空哦，没有空气 ，okay? Maybe there is no air, or maybe your electric field is inside a wall, or maybe inside a glass. You know your electric field can pass through something, but not metal, right? I think we have that common sense, right? So those four equations are general equations for every electrical field and the magnetic field. So they are supposed to write down every conditions. Okay. One of the condition is what is the medium? Where are your E and the H field? Where are they? If those are in the air, you will say, oh, I use some notation about epsilon 0. This is something about the electric field E between E and D. It depends on the material. Okay? And for the magnetic field, there is another notation we call mu 0 or mu. If you say mu 0, it is for air, and the mu is for some special material. Okay? We will talk about materials after we finish the simplest part. After we finish the simplest part, which means our E and the H field are in the air, those are the simplest part. After that, we will talk about materials, maybe dielectric material and the metal, different materials. They will have different answers. Okay? But at the beginning, maybe you can consider these two equations. Those are the relationship between B and H. Also, the relationship between D and E. Okay? If you have different material, even you have the same H field, you have the same E field, they, in a different material, they have different B and D. We will come back later, okay, we'll take a rest. Okay, anyone, if you got lost, you hurry up and come to me, and like a test or this part of the course. Okay, okay. Fundamental things. Okay, try to review the definition of capacitance, and this is a capacitor. We have two plates which has positive charge and negative charge, and the total charge is the Q here and the minus Q here. Okay? The difference of voltage between these two plates is delta V. This is the capacitor. Okay, you guys know capacitor. Then actually, because there are two plates, you can regard those are the accumulation of. When we talk about there's one charge, you will have an electric field, right? If there are two plates, these two plates has the positive and the negative charges. you will have a lot of uniform electric field between these two plates, right? Which means we store energy. We store in the form of electric field. We store our energy in the form of electric field between these two plates. Okay? The definition of capacitance C equals to Q over delta V. This is the fundamental definition of the basic. If you have two plates, positive Q and negative Q, and the potential is delta V. Okay? This is not what I want to say. I just want to say this one. This is a thing I try to say. If I have a current and there is the wired lines. This is an inductor, right? My current passes through this wire, then goes out from here. You will have because of the Ampere's law. You guys remember Ampere's law? If there is a current goes through, there will be a magnetic field around this current. If you put this wire line in this form, looks like an inductor. This is a structural inductor. You will have okay. This is the magnetic field go through the middle. The strongest magnetic field is go to this direction. Okay? This is Ampere's law. You store your energy in the form of magnetic field. This is the inductor. The equation of inductor is, I write down here, L equals to, it is sum, how many lines here? Those are flux density, right? And divided by current. Okay. What is flux density? How can I count how many green lines here? How? I don't know. No, I'm sorry, correction. I need to correct. How can you correct the flux, magnetic flux? This notation is magnetic flux, meaning there are some imagine lines. There are a lot of flux goes through this wire, this inductor. There are some imaginary lines. We call it flux. Okay, how to say that in Chinese? Flux.
那个磁通量。
Oh, 磁通量. Okay, the magnetic flux. Maybe some of you learned this before. Okay. Depends on what is it. This is the way we look at this inductor, right? But if we look at the inductor in this direction, if we look at this in this direction, you will see something. From here, you see that this way, right? Because every how to say, they overlap by each other. Then you will see that, right? Okay. And there will be a area. This area of a circle. You can see the area of circle. Okay. The definition of B equals to flux divided by S. I use very general one. This is not very accurate. It depends on your geometry or other things, okay? This is flux density, okay? It is a vector. Remember, when I say vector cannot equal to a scalar. And maybe this one will be, maybe there is a direction. Oh, okay, I don't care. It's not the most important thing. The direction of S, there is some direction of S. We sometimes we will define the direction of the surface is some direction perpendicular to the area, perpendicular 垂直. Okay, so this is we talk about only the magnitude. 大小, we talk about only magnitude. This one will equal very well. This is the flux density. What I'm doing here is I'm trying to explain this one. What is B? Okay? B is the average. It is the average flux goes through some area. This is a flux density. Density 就是密度，面积的密度。Okay? Flux 有多少 ？How many flux, magnetic flux goes through the area? Okay, this is B. Okay, which is related to our H field, and the H field times the mu zero. Okay, something is good is if you are in the air, you just remember mu zero equals to 4 pi times 10 to the minus 7. This is a constant. Every time you see mu zero, especially in your midterm, you need to give me the number and do the calculation. You are not allowed to just only use mu zero, okay? Give me the number, okay? Okay, this is a constant for the air. Very similar to between D and E. The definition of D is the electric flux density. Okay, I try to explain. I use the simplest way to explain those notations of the Maxwell equations. Now we can see the total. You can see the whole, the overall view, the overview of the Maxwell's equations. As I said last week, why I don't use the normal E, why I use the ugly E here. You can read your textbook in the POSA. They will tell you that because this E is the time-varying form. Your electric field is a function of time. Your H field is a function of time. Okay? You got it? It is not only a function of position x, y, z, but also time. You need to consider time. So use the ugly form. I don't know how to say that. Is that what is it between this form for this form? Do you have some formal way to say?
The special characters.
Special?
Character.
Special characters? That's it? I think it's like a typewriting or I don't know. Okay. Allow me to use a little bit Chinese to explain. 不同的字形它有不同的意义啊。这个写这个很简单，因为它不考虑时间。这个东西我连时间都考虑进去，它也可以符合这个事。OK， 那我写成草写，我要草写，英文怎么讲？ I forgot how to say that. Instead of okay, special. Okay, you can say that. spatial form. Okay, those are the spatial form. You consider not only position but also time. Those are important, but you don't know why important because you don't have the question yet. Okay. Okay. If I take the curl of your time varying E field, this one will equals to minus, I will take the partial differential to the t to the function of b. You know this one, right? You learn the calculus. Okay. Which means your b is also the function of time. Okay? Minus capital N. Still the spatial form, capital N. Okay, let's read the definition here. B is magnetic flux density, as I said, and you can see you can always see the unit to understand what it is. Okay, you can read the unit. It is the magnetic flux. The unit of magnetic flux is Webb, WB, Weber Webb, divided by the area, the unit area, m squared. Okay, so this is the magnetic flux density. Okay, this is B. And what is M? There is a good news. M doesn't exist in this world. Why do, if the M doesn't exist in the world, why do we need M? We want to make them beautiful. Because E field and the H field, they are like a couple. Okay? Like a yin yang, something like voltage and the current. They have a lot of similar equations. You try to make this equation looks very similar. Okay, so we will start from here first. You take a curl of the magnetic field equals to the partial differential respect to the time domain to the D function. D is the electric flux density plus J. What is J? J is not important. You need to remember because J is the current density. What is current density? Your current divided by your unit area. Okay? I think maybe I say something wrong. The definition of current is not divided by the area, right? It's just some charge passed through divided by time. That's the definition of current, right? I maybe made a little bit mistake, but it's okay. You know the definition of J is current over area. Over there is the area you pass through. So this is J. J has, this is a vector. Now you should remind yourself every time when you see the equation, you need to know which one is vector, which one is scalar. It is important. Okay? So now we finish these two equations. I introduced those notations. And then there are two more. Those are easy. You take the divergence of your D will equal to a scalar, which is the electric charge density. How many charge in the volume? How many charge in the space, in the volume? Understand? Divided by m cubed, the cubic of m. Okay? The power 3 means it is an area. But you divide it by the power 2, it means it's a surface. Okay? Yeah. it is okay that you still have no sense about these four equations if you forget or never have any chance to learn Maxwell equations. But then I will introduce why you should know these four equations. Okay, we will use this again and again and again. First of all, maybe we can do some exercise. So here. Anyone want the extra type? Okay, maybe I can do that for you guys. You can find there the back part of your textbook. There is an appendix about the theory. This is a vector theory. Just don't worry about it. If you don't remember that, it's fine. But if this question show in the midterm, maybe you should understand. You should know where you can find the equation, okay? There is a rule. If I have a vector here, I take a divergence, okay? If I take the volume integration of this result, this is a scalar because you already take the divergence of the vector. This is a scalar. You take the voltage integration of that, the result will equals to you take the same vector equation, you take only the surface equation, the surface integration of this vector. Okay, I just try to explain this equation. Okay, so I can write down. No, I don't want to write down. I want to write down. This is the equation. Those are Maxwell equation, right? I call this number 3 equation. I take this equation. I just directly write down if I do the D equals to the charge density, electric charge density. Okay, I just write down. I didn't do anything. Don't be scared. I just write down this one. Okay? Okay. Then I try to do the volume integration to both sides. Okay? What will I? Well, how will I get? I will take the volume integration. I just directly write down d v and v to the left side will equals to dv. V is not the velocity, it's the volume. Okay? I just put this part and this part here. I didn't do any special things. Don't worry. Okay? Second, because this part can transfer to this form. So the left part can change to, okay, anyone volunteer? Write down. I didn't ask any question so far. You want extra point, right? Raise your hand to write down left part. Anyone? You don't understand? Extra. You guys know every time you raise your hand, there are 3 points. You know that, right? I said that. Anyone want to try? 3 points. I want you to finish. Except that maybe you don't understand. You are not follow what I'm doing. No, you don't know? Do I need to do that again? Let me do that again, okay? You guys are shy or too easy to answer, or you don't understand. Okay, just use your finger. 1 is I'm shy. 2 is sorry, I don't follow. 3, just 1 or 2, okay. 1 is you are shy. 2 is you don't follow. 3 is too easy. Okay, 3 is too easy. Okay, show me your finger. Now, I want to. 1 is you are shy. 2 is you don't follow. You're shy. Okay, about. You don't follow. You don't follow. Many. No. Okay, okay. Do you want to just take a point? It's good for your fellowship if you can try by phone. Okay, so. I encourage students to be more active. It's not only good to learn, but also to your future career. You should be more active. Maybe I'm too fast, right? Too fast? Do you have a question mark? Which one equals to something or? Well, if you know it's fine because you are the only one who can answer. But there's supposed to be what something equals to something, right? Yeah. But if you want to write correctly, you want to try or think more. You guys understand now? No? Not yet? No. You don't follow, huh?
上台是在写什么？
就是，对吧？ It's okay. It's okay. It's okay. Okay. I repeat again. If everyone cannot follow, it's my fault. Okay? I repeat my question again. Okay? First of all, these 4 equations, Maxwell equations, they are just the most important rules from the beginning. So I'm not going to change anything. Okay? Those are the beginning. You just you learn this from other classes. I'm not going to explain too much. I already explained some of them, but they are deeper than that. So if you don't understand, that is okay. I'm going to teach the things after you already knew Maxwell equations. Okay? So, at the beginning, what we are going to do is I just copy this equation. Okay? I copy the third one. I didn't change anything. Okay? Okay? I want to change the form. So, what can I do here is this part and this part. If I take the volume integration, 中文是体积分，左右都 take volume integration. If I take the volume integration, on the left side, the result will equal to I take the volume integration over the right side, right? If I do the same thing to something they are equal, the result will become another something still equal, okay? Okay, so I take the volume integration of the depth part. Maybe some of you are scared about this one. Those are integration. I don't care what it is, but I care about it is the volume. This will be a function, then I take the volume. How to do the volume integration? You don't need to worry about that. You just write it down. You take the volume integration for the left part. Okay? Equals to, if I take the volume integration to right part. Are we okay here? Okay? Okay, no problem, right? If you take a volume integration here, maybe I try to explain this at the beginning. This is what is the definition of this load? The definition of this load is the electric charge density. How many charge in a volume? 在一个体积里面有多少的电荷 ？Okay, it's okay. Nobody will see. Okay, it's okay. If you can understand, it's fine. Okay. This is the electric charge density volume. How many charge divided by the volume? Volume 是体积，你知道哈 ？Volume. Okay, volume. Okay. So if you integral this one to v to your volume, v is not velocity, 不是速度哦，是体积哦。Volume. Is that correct? Volume. Okay. This one will equals to Q, right? Are we okay? Are we good here? Okay. The right hand part will become Q. The problem is left hand part make no sense to me because I don't know what is the divergence D. Take the volume integration. I don't know what is that. I don't know. So there is a relationship. There is a theory about if you have a vector, you take the divergence, then you take the volume integration, this result can directly change to a simple form. You just take the surface integration of your original vector. That's it. Okay? Use this relationship to your left part. The question I ask you is, so this one can become the owning vector function D here, take the surface integration dot S will equals to Q. This is the thing I'm trying to explain. So the third equation, you take the divergence to the D equals something, can be explained in a different form. This is a differential form, 微分形态. This is the integration form, 积分形态. These two equations are totally the same. It depends on how you read it. Okay? Maybe you don't get any sense about this equation. Maybe you will have some sense about this equation. What is this equation? This is our Gauss's law. If there are some charges in some space, you take a closed surface integration form to this charge. The result will equal to your total charge divided by your epsilon. If it is air, you just divide it by epsilon E. You can move your epsilon to this part, and this one is D, right? This is electric flux density, right? You take a closed form of the surface integration of your electric flux density. You will know how many charges are inside this space, are inside this surface. This is Gauss's law. You guys know Gauss's law, right? No?
First time.
First time? Uh-oh. Okay. Okay, it's fine. If you have any question, maybe you should Google it, but because we still have we still need to go on. Okay? But I believe I spent enough time to explain. Okay? If you have some question, maybe we can discuss later. But this is one of the important rules. You take the integration of the D, but you should remember this is the close. You need to make it close. You need to integrate everything of the surface field. Then you know how many charges are inside. Okay? Okay, this is the first thing you have to learn. More a little bit hesitate. Okay. So we can finish that. For the number 4 equation equals to 0, which is good for us. So if you take the integration of the magnetic flux density, always equals to 0. Okay? Magnetic always equals to 0 because there is no magnetic charge in this world. No. I just make it looks beautiful. They just make it looks beautiful. There's no discharge. You have only the electric charge, right? You don't have you know there are magnetic dipole, but there's no magnetic charge. Okay. There are more and more serious about that. I just want to give you some common basic knowledge about that, then I can go on. Okay? Okay. You can discuss with me, but if you go too far, I will tell you that you just stop. Those are not relevant to our class. But for this part, I think it can understand. It's understandable. Okay. So what is important thing here is you take an integration of your electric flux density will equals to Q, and if you take this one, it will equals to 0. Those are Maxwell's equation in the integration form. Integration form, yeah. This is a differential form. This is integration form. They are the same. They are the same. And because most of you don't know Gauss's law, right? Anyone heard this before? Gauss's law? No? Yeah, you know Gauss. This is common law, right? Yeah, it's very, very common law. But I think, yeah, if you don't know, that's a good thing. Now you know something common. Yeah. Okay. We can continue. Yeah, especially for students in electrical engineering or electronic engineering, everyone should know this one, the Gauss's law. Okay, another 2 more rules. You understand the first one? Can we go on? Can anyone want to do this for? We can That one, the Gauss's law is simple. This one is more, they have more components. We have more. So, okay, let me apply. Do anyone want to try this one? To get an extra pi? Do you want to try again? Abi? No? Okay. Okay. Actually, we are doing very similar things. But I do that again in different equations and they look very similar. Do very similar thing. Okay. If you cannot follow, it's fine. Maybe because I teach too many years, I taught too many years. That's why I don't think that's much difficult. But maybe for you guys, I hope you can follow. If most of you don't follow, maybe they will show in your midterm exam. Okay? Okay. You don't know, then you know, then you learn. You can convince me that maybe okay, you can pass it because you learned something. You need to convince me that. Okay, I will do that again, but you please engage. Please keep focus on what I'm doing here. Okay. Okay, I will keep in mind. Maybe this one will show in the exam. Let's do that for. Do you want to do for the number 1 or number 2? Let's do the second one, okay? Let's do the second one. If the second Maxwell equation will equals to this is d dt plus this is j, okay? I just copy my second equation here. Alright? Okay, now this time I will do that faster. I use different color to help you to understand. I try to, because we know this relationship, so I try to check the surface integral to both sides. Okay? If I take the surface integral to this part, I will obtain maybe you guys don't understand because I use the same color, right? How about this? If I take this one, will equals to, I take this outside, then I will take the surface integral to D and ds plus j Are we good here? Okay? I didn't do anything. I just copy the equation and I check the surface integral to both parts. I think this color can help you, right? The blue one and the orange one. Okay, the orange one is the same, and I take it to both of them. So this is the current density, as I said. Current density is current divided by the surface, right? The area divided by the area. So this part can become current Okay? Okay? If your D is not changing according to T, if D is not changing to D, you can omit this one. You don't see this one. If D is not changing, but I know at the beginning we said D is time various, right? But in the case of D is not function of T, you don't have this part, okay? Then, how about this part? You take something curl. You can use this one. You take something, you take the surface integration of something curl. This one can become, maybe I need other color. This one, that part will become, anyone? Ah, good. Now you understand. Yes. Somebody understand.
I'm not sure.
Just write it down. No, that's L.
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 But you can take the point. Okay, good, very good. Okay, very good. So, if there is an H field, this is a close integration. It is a linear integration, 线积分. But your line should be a circle. That doesn't matter is a beautiful circle or not. You need to be close. If you take the integration, the linear integration, and this is a loop, is a closed form, U equals to current, which is something we call Ampere's law. We miss something. Where do we miss the? Yeah, you don't miss anything because you can divide V by mu and become H, right? You move the mu to this part. You know the Ampere's law. Okay, I think everyone knows this one, right? Ampere's law. If there is a current, you have a magnetic field. Now, you integrate the magnetic field, you know the current inside. Okay? So, we prove that the second equation is Ampere's law. Okay. The most difficult thing is this first one, but actually things are very similar for this one. You still do the same thing here, then you can get a result which is this one, this equation. This is the Faraday's law. If you change the magnetic field, they will give you the induced electric field. The induced electric field dot by your line, the circle of line, will equals to your EMF, which is the same as how much the B field, the magnetic flux density change on this area. This is Faraday's. I think you guys have some, you know this is the electric magnet, right? You change the magnetic field, they will bring you current. Okay? when you change, you use some different technique. You change your magnetic field, which means this term. Your magnetic field is changing according to the time. And this one will become the EMF. You just ask me. You say EMF, right? This is what you are trying to say. If you change the electric field, the magnetic field, you change that, they will bring you the EMF. This is an electromotive force. This is, I think this is the, is that a fundamental theory about a generator, how to produce the electric, how to produce your current. You try to change the magnetic field, you will give you an induced E field. Okay? So I will make a conclusion before we take a break. The conclusion is these four equations are not special ones. Those are Faraday's law, Ampere's law, and the Gauss's law. Those are very common, very fundamental theories. These four fundamental theories, no? Never see this before? Maybe you see different form, or maybe they have different consideration. Those are very useful in many different fields, maybe in physics, in electric, magnetic, or other. I think those are very, very useful, but depends on you have different notation and different situation. You have different considerations, but actually, basically they are the same. Okay, let's take a break, and I can explain if you guys don't understand. Okay, 下课. Okay. Okay. Let's do more. When last semester, I think you are the only one who didn't take the射频无线通讯系统, right? And also Abi, you didn't finish your RF wireless communication system. Let me do a little bit review about what we are doing here, why we need the microwave engineering, and I will bring you back time harmonic, okay? Why I can use the time harmonic. When we are trying to, the most application, the popular application of the microwave engineering is we trying to make iPhone. We trying to make part of the iPhone. We call it wireless. We call it a communication. Wireless communication. Okay. How can that work? How can we make the wireless communication? There is nothing there. How do we communicate? We know usually we see the movie. We know we use sometimes they will use some detective. They use maybe the Morse code. Is that correct? Morse code, 摩斯密码, right? We have the rules. Actually, that is a protocol. I know if this is not true, but I try to just have an example. Something long or something short, then under our protocol, 在我们的协定之下 we know what is A, what is B, what is C, what is D. Then we can use some message, I can transfer my message. Like what I'm thinking here, I use English to let you know. You can understand what I'm thinking here. It is because we have the same protocol. When I say English, you understand English, right? This is language. We do the same things in the wireless communication systems. And bring you back to, no, that's a master. We will have some data. I try to send some data. This data will transfer to a form of microwave or maybe a EM wave. This is the wave we are talking here, E and H. I say this is encoding. I hide my data, I hide my message inside this field. According to the antennas and the machines, those are TX and RX. Finally, I receive some EM, E and M, I receive some energy. And I transfer this energy according to the protocol to the original data. Then I can understand what you are talking about. This is the fundamental idea about how to use the wireless communication system. Okay? This semester you guys listen to in Chinese maybe easy, but I say it again. Okay. Those signals, I call it signals. We usually hide the signals into the. It depends on the different coding or decoding. 调变 different coding and decoding. We discussed like Q, P, S, K, right? Different coding system, right? I think maybe many of you, if you forget, maybe you can take the class again. It's okay. Yeah, to remind you, or maybe you never learned this one before. You always use the signal. The signal, the basic signal, is based on cosine function. This cosine function, you can see that in the oscilloscope, maybe 示波器. Okay, you see oscilloscope. You can see this cosine form in that one, right? Those are the carrier. The carrier. You hide this information inside that one. What is the general formation of this cosine? This cosine function will repeat, right? Will repeat again and again and again, right? If this information is repeating according time again and again, we call this time harmonic function. Okay, I try to explain these two words. Time harmonic, because we are dealing this cosine function. Okay, in our class, in that class, we always say we use the signal. We use cosine omega t. It's changing according to time. Omega means 2 pi f, right? Because it's an angular frequency. You multiply your frequency to 2 pi. Your signal repeat in 1 second, that happen f times. Do you understand what is the frequency means? The fundamental definition of f means how many times a second. 多久 ？It's
1秒钟多少？
1秒钟发生了几次 ？This is the definition of f. Okay? So, if there are lots of the cosine wave in 1 second, those are 10 to the power 9 times, which means your f equals 10 to the power 9. Okay? Okay. Then, it's repeating in 1 second, it's repeating so many times. Every time the same. It's repeating again, again, and again. And that is time harmonic. In Chinese, 时谐. Okay? If this is time harmonic, in our last class, I think maybe I explained clearly that we can use the exponential j omega t we can use this one to talk about the real part and the imaginary part. We use this is the phasor form. We talk about the phase of the time. You remember this one? If no, you use the Euler cosine omega t plus j sine omega t. This part is the real part. This is what I draw there. This is the thing you can detect. This one never happened. It's helping you to calculate. We discussed in the AC power. Last semester, right? I think most of you already understand. Or maybe you try to review. You can check my website to review the thing, okay? So, we use this part. This is the only, remember, if I said that, you follow it. This is the only component of the time. It's a good thing. When I say this function, it is time varying, which means the time may be changed, different things, it's very hard to define. But once I tell you that this E field, this H field, those 4 equations are in the time harmonic situation, if I said that, you can directly use this part. You guys know J is I, right? It's the imaginary part. The cube, no, not cube, the square of the J equals -1, okay? E to the power J omega t, this is the only part relevant to time. Okay? Do I need to use Chinese to say it again? Pardon me, okay? I think their eyes tell me that, please. So, 我们一直在说这几个用草写写的符号是有时间变数，但是时间变数有非常多的可能性，但是你只要知道它是时谐的，随着时间会重复的，我很简单，我就只要把它乘上这一项就可以了。所有的剩下的人都跟时间没关系，这样你就把它拿出来就好了。OK？ Okay, totally the same thing. I just use Chinese and English. Okay, try to follow up. Okay, there is no more information. I just say you just take this part out. There are no other component. We are talking about time. Only this part. Okay? One thing very useful is, and you can continue. Are we are taking? Okay. Okay. You are taking, right? Okay. One thing is important is if you can take this part out, you know if I want to take the differential respect to time, because we have only corresponding to this equation, what is the partial differential of this equation? You just take jt, you do partial to t, this one will equal only j omega, right? Times the external. Do you understand that? I think all of them, you saw this before, right? Many times. This happened only for time harmonical case. Because time harmonical case, your time only relevant to this equation, but you take this equation to the partial differential to the time, this one will equal j omega times the determination j omega t, your original equation. Okay? Because other parts, they don't have a time component. This is the only way you can do that. Okay? Okay. So, eventually, we can transfer this spatial form to this. Maybe it's more comfortable form for me. I can write it in the usual form. This form is more common to see. Okay? So, when you change all the character from the spatial characters to our normal characters. Okay? Second, if you see the partial differential derivation respect to time, you change that to j omega only. Okay? And this is a phasor form, differential form of the Maxwell equations. And you are asked, you should remember these four equations again and again. At least because we will have only the open book test, right? You should always know where they are, okay? We will use these four equations to many things in this class. That's why I spend so much time to explain these four equations. And I use a red star here. Okay? If you take the curl of the E field equals to minus j omega times the magnetic flux density minus m. The m is the magnetic current density. You will see you will see a definition. But the thing is here, it's no time. There's no time issues inside. And then if you want to consider back to some equations relevant to the time, you just directly multiply your equation to exponential to the j omega t. Okay? Okay? Are we clear? Okay, so beautiful four equations here. Then we can start our class. I think in your textbook they start from these four equations directly. Or maybe they start from here. Then he discussed about the time harmonic, and then we will have these four equations. And the book used these four equations again and again and again. Okay? Can we continue? course. We still have time. So, after I introduce the 4 Maxwell equations in the differential phasor form, differential， 它有积分形式跟微分形式。This is a differential form, and it is a phasor form. Okay. Okay. Boundary conditions. What can we do? What can we do? After we know these 4 equations, the first thing in the textbook is trying to explain boundary condition. They try to explain a question. You can see that what happened here. We think about, try to understand what they are talking about. Faraday's law, Ampere's law, Gauss's law, right? Remember, there are 3 to 4 laws because there are 2 Gauss's law. Okay. They try to explain if we have the source, the electric source or magnetic source, what is the E field or H field? I'm talking about the beginning of these 4 equations. If I have an E field, if actually we can do it this side, this is Faraday's law, right? If I have M is the magnetic current density, which is a source. We have the source, current, magnetic current source here. And we change the H field. We change the B here. Then this one will introduce you the electric field. They will come together. Okay, this is the thing we try to explain here. Also, if there is a source, I have a current source, I have a current, they can introduce you a magnetic field around that. This is Ampere's law, right? This is a source, this is a source. Or maybe I change the H. This is also something like a source, right? I change the field, okay? Okay. Gauss's law. If I have a charge source here, then they will have an electric field outside the charge. This is the third one. I have a source, I have a field. I have a source, I have a field. I have the magnetic source, I have an electric field. I have an electric source, I have a magnetic field. I have an electric source, I have an electric field. They are coming together. I'm talking about owning the source here. What are the field? What are the E and H field around this media, around this area, right? Okay, this is basically the fundamental theory about the Maxwell equations. But, there's always but. If I have source come with, I have an E and H field, we have no question. I already explained everything that. What if, it's okay. What if I have E and H field in the air? Okay, no problem. I can explain that by these 4 equations. What happened if there is a boundary here? You have air up to this boundary, but down to this boundary, we have something different. what happened? You can tell me that all of them they can use different Maxwell equation, right? Because you can use the you will tell me that if you already understand what I'm talking about, you can tell me, oh, you can use different material, you use different constant. If it is air, you use mu 0, epsilon 0, right? If this is not air, maybe you use epsilon 2 and the mu 2, or maybe you just rename that epsilon 1, epsilon mu 1, and epsilon 2, mu 2, right? You can use that. I already told you, different materials, different mu and a different epsilon. You can use that. Okay. But how about this line? Maxwell equations are always right. There's no exception. They can always be right on this boundary too. Understand? Understand what I mean? You need to obey Maxwell equation upon this boundary. You need to obey the Maxwell equation upon this boundary, but they have different epsilon and mu, right? What happened on the boundary? That's a question. You should still be correct on the boundary. Okay? Do I need to explain in Chinese or you guys understand?
What is boundary?
Okay, that's Chinese. Okay, pardon me, sorry. I think they to how can this can be true for boundary? This is it, boundary condition. Okay? Yeah, this is what I'm trying to tell you. And this is what they are telling you in this part, okay? Boundary conditions. Yeah, this is interesting, right? This is true, this is true, what happened here? They should be also true. Okay? Okay, let's continue. Yeah, the thing is, you have different mu and different epsilon, right? So, actually, you have different mu and different epsilon. There are something different. There are something the same. This is how we use that to solve this equation. There will be something different and something the same. Let's look at that. So in the book they tell you more general things. If that is a linear media, actually mu and epsilon, it is very simple result that in this part you use mu 1, epsilon 1, epsilon mu 2, epsilon 2. But in the real world, that's not correct, right? Maybe this will be a function of the position. Mu and epsilon may be a function of the location. And also, mu and epsilon, it is a function of the location. It is not linear. But we simplify the question to, oh, it's linear, so mu and epsilon, those are just a constant, or just a number, or just use it. Don't think too much. But there are more deeper researches. They try to figure out what if mu and epsilon, they are functions of location. Okay? So, it should be good in this page. Okay. So, here we try to redefine our question. Okay, actually, in here, they say this is 2, and this is 1, no matter which one is 1 or 2. Actually, this is a definition. This is the media one, media 2, and the bottom one is the media 1. And the boundary is not necessarily a straight, a flat surface. Okay, it can be any. It can be very general. If the B field in the media 2 is Bn2, if we talk about only the normal direction of the B field, we use N is a normal. This B, this magnetic flux density is perpendicular to the surface, okay? And we also use the Bn1 here. They are in the same direction. And also HT2 and HT1. T means tangent, right? Tangent, 切面 tangent. 这个 normal 是就是垂直的 ，okay? So you regard your surface, you think like you consider only the normal direction of B, you consider only the tangent H field, you will have HT2, HT1, okay. And the direction normal to perpendicular to your surface, you will have the unit vector N perpendicular to the surface, 单位向量. Okay, it's not necessary. It can be X or can be Y or can be Z. But in the textbook, you want to explain this as general as possible. That's why I use N. Maybe N is X, maybe N is Y, maybe N is Z. Maybe N is the combination of X, Y, Z, any direction. Okay, not necessarily equals to X, Y, or X or Z. Okay, and okay, and ET or also the E field, tangent E field in the media 2, media 1, and normal D, Dn2 and Dn1. And there are sources on this boundary source. We will have the Js, which is the current density, and it is I think it's a linear current density. Current divided by I remember it is a line, one dimension, 它是除以它的一个长度的。The current divided by one dimensional line, and rho s is a Q divided by it is a charge divided by the surface, the area. Okay, it's also rho s is a charge density, but it depends on the area. 面积的浓度的那个 charge 的那个叫什么？中文叫电荷，都带电量。Okay, and ms is something actually not happened, but we also write it down because this is a magnetic current density. This is the electric current density. Okay, those are the equation, the situations. Before we start, we try to define different vectors in media 1 and in media 2 and in media 1. We try to write everything down. Okay? You guys, after you have the textbook, you can check. I'm here try to help you to understand what textbook said. Okay? This is a picture from textbook. You will refer to textbook after that. After you update your textbook. So first of all, we consider the Maxwell equations, the phasor from differential Maxwell equation. We consider the third one and the fourth one, these two equations. Okay, we think about that. What happened if, do you remember what are those? Can anyone tell me? Okay, one more extra points. Anyone? Raise your hand, tell me what are those equations? Or maybe what is the physical meaning about the Maxwell equation number 3 and number 4? Anyone?
Gauss.
You guys got those? Anyone?
Gauss.
Who?
Gauss.
Hmm?
Gauss law.
Gauss law, yes, that's correct. Okay, and get extra point, like him. Two of you, okay. So what is the Gauss's law? Can you explain what is the Gauss's law? Do you remember?
If the current is flowing in a direction, there is a magnetic field around it.
Again?
If current is flowing through, if current is flowing, there is a magnetic field around it.
That is the Ampere's law. You want to repeat it? What is the Gauss's law? Yeah, the third one is Gauss's law. Right? Yes. You talk about current, right?
Yeah.
This is current density, right? And if there is a current, you will have a magnetic field. This is Ampere's law. But very close and very good. Do you want to try again to explain the Gauss's law? Do you remember what is the Gauss's law? Or maybe I can show you the picture to help you. Gauss's law. You want to try? We will give him a little bit more time. You want to explain? Try to use your way to explain to other classmates. Maybe it's too hard, but it's okay. Just try. Just try. You can read again and use your word to tell other students. Gauss's law.
Is the in an enclosed surface the number of charges we have that's divided by the epsilon, like epsilon of that surface?
Yes. Okay. Very close. Okay. I will give you a point. I know maybe. Do you want to try again? In different way, or you maybe? Okay. I give you another opportunity. In Chinese? Okay. Okay, maybe it's okay. In English and in Chinese, you can help other students understand what is Gauss's law. Okay, go
那
on.
个封闭的那个表面里面，内附所含的电荷会相等于外面它所散发出来的那个电荷怎么样？会相等。
Very close, but there will be little something. Maybe you can read the equation. There is a closed surface, right? Will equals to the integration of, what's that? With times epsilon into here become d, right? Will become the integration of d is, do you remember what is d?
Density. Current density.
What current, not current density. Start from F.
Flux density.
What? Electric flux density. Okay, very good. Both of you can get an extra point. Okay. Okay. Let me repeat again. Gauss's law means if there are charge in some area, you take a closed integration of the space. You must be close. You must to encounter all the space. You integral all the electric flux density D. You will obtain Q. You will notice how many charges are inside this surface. If there is no charge, let me show you that. If there is a charge here, right, we will have a current density. I use 2D to explain. I integral this part, you will know the Q. If I integral this part, you will still get some answer, but because in and out, they will cancel by each other. The result will become 0 because there is no charge inside this area. Okay? This is Gauss's law. Okay? Okay, very good. I think both of you good. Yeah, probably you think this is too much, too hard.
Yeah.
But I think probably it's because there are too many things in your first time, right? It's not hard, but too many details for your first time. That's why you cannot remember. It's fine. You will have your textbook. You should review, read some book, and we will discuss. We will use that again and again, and you will understand. That's how we learn, again and again. And that is why we should learn this. It is because this is difficult, right? Right? Even you have book, even I speak 1 or twice or 3 times, maybe you just try to understand, but it's still hard. And that's why it's worth it to learn. This is why it's worth it to learn. That is too easy to learn. We don't need to take this task. Okay. So, yeah, I don't know if I can finish the boundary conditions. We have just a little time. Okay, let me just do a little bit more, and I will stop here, and all of you go back to think about that. Maybe I will have an exercise next week to discuss this, okay? And after you get the book, you can read the book and then think about this question. Okay, a boundary condition. We think about a special case of Gauss's law. There is how to say that? Cylinder. Okay, this is a cylinder. 圆柱体. Okay, if the area you guys are talking about, the area we try to integrate, it is a cylinder. Is that okay? It can be any surface. The only thing is it should be closed, right? It should be enclosed. 它必须是一个封闭的平面。它可以是一个这个圆锥体 ，can be a cylinder. Okay? If this is a cylinder, I put a cylinder on the boundary. Is that okay? This is a 3D, okay? Because it's a cylinder. 3-dimensional. Use your imagination. 3D. But I have only whiteboard in 2D. So you need to imagine something. If this is a cylinder, spatial cylinder, how spatial it is? The height of the cylinder h is 0. It is 0, but not 0. Very close to 0. It's a very flat cylinder. OK? 它很扁的一个圆柱体。它的 h 呢接近0，但是不是0，很接近0。OK? Is that okay? We can also do the integration of all the surface. Remind you that you should notice that if you integrate all the surface for a closed area, the result will become Q, right? Right? Okay. What happens if H goes to 0? What happens? Anyone? Another chance to get the extra point. What happens for a cylinder if H goes to 0? What happens?
We just calculate the surface area
Which one? Of
4 pi r square
of
the circle.
keyword is I need some more, but you already have the extra point. Maybe we could, somebody will have the opportunity, okay? 有没有人要解释一下，要讲一下？你觉得它会变成什么？ what happened if h goes to 0 but not 0? What happened about a surface? What is the surface? We will consider only. You want to try? Anyone? We will consider only maybe Abby already give us an answer, right? I think you are correct, but because you already know the point, so you will consider only this surface and this surface. Because you don't have the height, right? It's very flat. You consider only this plane and this area and this surface. Only two surfaces. Yeah, you basically right. Okay, but there are two surfaces. For the medial 2, you consider this one. The medial 1, you consider this one. Okay? What are the difference between these two surfaces?
Epsilon. Epsilon.
Epsilon. You mean very close. I know you understand. Now you are following what I'm talking about. Yeah, I want you to do that. Don't be shy. Tell me what's are different between your answer is close but not accurate. Anyone? The direction of these two surfaces is the same or different?
Sir.
Huh?
Sir.
This is to this. The direction of surface is the direction perpendicular to it, right? To the surface. So for this one, this part is going to up, and for this part is going to down, right? At the beginning, we defined D, the two D in the same direction. So eventually, if you do the surface integration of D, you will obtain these two electric flux density should D2 should minus D1. Why D2 minus D1? Because D2, the direction of D2 is the same as N, but direction of D1 is opposite way of the N, so this one take to the minus part. And you can read your book and try to understand our original equation that if you take the integration of the two surfaces without a height, which means you have only one surface and another surface, times D will equals to Q. Or you can take the surface to this part. You will have the left side will have only this part, and the right side will become Q divided by surface. And this one, we define this equals to eta s. This is another charge density. Okay? Think about that. Buy your book and read the book. Okay? Okay, we will stop here and we will continue another boundary condition next week. Okay, see you next week. OK， 听得懂吗？看你们都快睡着了。
老师可以解释一下那个。